Hi guys, today we'll be looking at uncertainties. Until now, we looked at propositional logic and predicate logic. We were looking at events that were either occurring for sure or not. But we as humans tend to show our intelligence in cases which cannot be totally polarized. For example, when given two roads to reach a hill station, one which has a muddy road, the other one which has a tar road, you definitely pick the tar road because you know you're less accident prone when you take the tar road. That doesn't rule out an accident on the tar road, but the point here is it is less likely for you to get into an accident, and so you choose it. A computer also needs a capability like that if it needs to be called as an artificial intelligent one. And then this can be achieved by using either probability or fuzzy logic. A lot of you have already finished your assignments on your own, so I'm guessing you're comfortable with the topics. You can skip directly to the end part, that is the assignment questions. If not, you can simply brush out your knowledge. I mean, the videos are not too big, so you can happily just scroll through them. So let's look at probabilities. So probability is very easy concept for you to understand. So here we have a big population. Let's say yes is a big population, and A is a small subset within that population. So the probability that A occurs within this big entire S is given by something like this. Probability of A is A by S. So pretty much simple. So in this chapter, we're dealing with two kinds of probabilities. One is joint probability, and then we have conditional probability. So what is joint probability? As the name suggests, so when two events A and B occur simultaneously, our interest here is to find out the probability that they occur in the entire population. So assuming that you have A and B as two independent events like this, the probability that both of them occur simultaneously is given by P of A into P of B. Remember that this formula is applicable only in the case of independent events. The formula changes a bit in the case of dependent events. So please be mindful of that. Anyway, so what are independent events? So you have your examples here. So the probability of getting heads on 2 coins, or the probability of getting at least one head, they're independent. So these are called as independent events. Anyway, so this is a formula that you guys are pretty much aware of from the set theory, where you know that P of A and B is given by P of A plus P of B minus P of A intersection B. Now, using our knowledge that we have just acquired, we can write P of A intersection B also as P of A into P of B. Also, you can rewrite P of A as P of A and B and P of A and B dash. That is, P of A can be written as the probability of A occurring along with B and the probability of A occurring without B. Similarly, P of B can be written as probability that A occurs along with B, probability that A does not occur along with B. So if you were to simplify this equation, you end up getting something like this. So this way, we can represent P of A and B entirely in terms of conditional probabilities. So similarly, we have P of A or B. Now how can we write this in terms of conditional probabilities? We just take complement of P of A or B, and then you end up getting this. Anyway, this is not really that important. So let us head on to our conditional probabilities. So this is the relationship between our conditional probability and joint probability. Now this right here is called as conditional probability. That is how you denote it. So H occurs after E, as in we are trying to find out the probability that H occurs given that E has already occurred. Now that is given by P of H and E divided by P of E. Now we have seen that if H and E are independent events, this thing is joint probability, and then you can rewrite that as P of H into P of E, right? And then you have a denominator here, P of E. So bring that here, both of these get cancelled, you end up getting P of H. So in the case of independent events, your conditional probability is nothing but one of your prior probabilities, like this. Similarly, you can say same things about P of E by H being equal to P of E, right? So in order to help you better demonstrate that, we have an example here. This is also present in your textbook. A few of you might have written it in your assignment. So here it says that the probability of any person chosen at random being literate is 0.4. The probability of any person chosen at random having age greater than 60 is 0.005. And we're going to find out the probability that any person chosen at random whose age is greater than 60 is literate. So here we are supposed to be finding out a conditional probability, which is this. In general, it would lead us to something like this: P of L and A6 divided by P of A6. So that is what you'll be having here. But since these two events are given as independent events, you do not have to worry about A6. That is, you do not have to worry about this probability here. This is the only thing that is of our interest here. So this can be written as 0.4. P of L given A6 is nothing but P of L. It's pretty much simple. Now I have a small question to you guys. A lot of you have skipped the question number 9.2 from your assignment, the original assignment. Even I might have gotten confused there. I told you guys to skip it. So yes, that's a part on my part. Anyway, now I want you guys to revisit the same question. Assume that those events are independent. So the question goes something like this. You're supposed to be finding the probability of a person chosen at random having age greater than 80 is female. So now I want you guys to assume that both those events are independent, and then I want you guys to come up with an answer. You have two more conditions coming up in that, 1 and 2. So based on that, you're supposed to be coming up with your answer. So this will be your first question in your assignment number 2. So that's it. Thank you.